Can you hear us? Okay. Maybe we can turn off the student mic. Try it now.
Okay. Doesn't trust me. No problem. So am I speaking to anybody?
You might just be speaking to the Zoom sometimes. They plummet through the Zoom thing and push up.
Okay, well, I'll try to compensate with my own physical resources. Yes, so as I said, this is going to be a somewhat lower level, and this will give you the opportunity to define freeness, since Dan Wojciechowski did not. So that's will free everybody subsequently to mention it again. So what's the main object that we're talking about? So we have an algebra A. The basic object of non-commutative probabilities, an algebra not necessarily assumed to be commutative, endowed with functional linear, linear functional, a linear functional tau defined on that algebra with complex values that takes the value 1 on the unit of the algebra, which we view as a generalization of the expected value. So A is what consists of the random variables, and tau is the expected value on random variables. And I'm also going to consider two subalgebras, A1 and A2 of this big algebra A, unital subalgebras. Examples of such things are L infinity of a probability measure, for instance, with the functional tau being the expected value. Another example, which is more congenial to us operator algebraists and the operator theorists, is B of H, bounded linear operators on a Hilbert space with, say, a vector state, omega xc, as is written there. And AJ could be just the algebra generated by some element TJ in the big algebra. Okay, so just a plain algebra or a weakly closed algebra, depending on the topology that we prefer to use, a star algebra, and so on and so forth. Okay, definitions. So we start with something classic. Oops. Now this is a sad situation. Okay. We have to place ourselves . Okay. All right. Thank you. Sorry about technical difficulty here. First of all, classical independence. Classical independence is a definition that is not usually stated this way, but let me state in this particular manner. Suppose that the algebras A1 and A2 commute, and if you have an element A1 in the big algebra A1 and A2 in the second algebra, with the property that their expected values are equal to 0, then the expected value of the product is also equal to 0. Yeah, so this is one definition of independence. So usually we use it, you see it as a product of traces, products of expected values, but I set it this way in order to make it more natural to give the definition of free independence. So what's the point of this definition, or one point of this definition is this one. Suppose, for instance, that the algebra A is generated by A1 and A2, and you understand perfectly well what the trace does on the algebra A1 and on the algebra A2. This formula allows you to calculate traces on the algebra generated by A1 and A2. For instance, sums, products, polynomials and elements in A1 and A2. One can calculate the distributions and the traces of those things in terms of tau1 restricted to A1 and tau2 restricted to A2. So it's a kind of a special position of the two algebras in the bigger algebra and relative to this particular freeness. Freeness is exactly the same condition, if you want, but adapted to the non-commutative setting. You see, if you just have the condition that tau of A1, A2 is equal to 0 when tau of Aj is equal to 0 and A1 belongs to A1 and A2 is in the second algebra, that doesn't allow you to calculate moments of more complicated expressions in the algebra, because not all expressions in the algebra generated by A1 and A2 are sums of products of the form x1, x2, with x1 in the first, x2 in the second one. You have products of more than two elements. And then you give exactly the same definition. If you have a product of several elements, each element is either from one algebra for the other, the traces are equal to 0, and the consecutive elements in the product are from different algebras, then the trace of the product is equal to 0. So that's freeness. So I put it this way so it sounds easy. Yeah, that's the. In both cases, you have the property that the trace of a product of two elements is the product of the traces of the two elements, or the functions of the expected values of the two elements, when the elements are from different algebras. So there's a commonality between these two conditions, but generally speaking, these are incompatible conditions. You cannot have both freeness and independence of two algebras. Yeah, so it's very seldom that only trivial cases, both conditions are satisfied. Okay. Why? So here I'm going to start with paraphrasing a published joke of late Frank Harari. He wrote an article titled, "Is the null graph a pointless concept?" So, and of course, the face answer to that is yes, it's a pointless concept. There are no points. The null graph has no points and no vertices and no edges. And in some sense, this is also true about non-commutative probability. There are no points. Yeah, so there are the probability space has disappeared in this context. Yeah. So, at least theoretically speaking, it's not there. But is there some point to it in the mathematical sense? Well, it may be that your algebra is generated by several independent or free subalgebras, and you understand those subalgebras, and you like to understand the whole algebra. Maybe that the little algebras are simple to understand, but the big one is not so easy to understand. So maybe there's a point to it. Then a third point is that classical probability concepts have free counterparts. There are many analogies that serve as a guide to some extent as to what one can do in the free case. The classical probability, there are classical probability objects that approximate free objects, and you have seen maybe not examples in Voiculescu's talk, but hints as to the fact that such things happen. So the most interesting examples come from or some of the interesting examples come from the theory of random matrices, where you have large random matrices. It often happens that they're asymptotically free. So the points come back to some extent. And there are many unresolved issues in these theories that keep us busy, and many other reasons that I don't mention. Okay. And I'd like to do a sample computation. Sorry. I didn't sleep very much last night, so you'll have to excuse me today. So if I say something that doesn't make sense, please point out to me that it doesn't make sense, and I will try to make it better. Yes, there's a sample computation that is going to come in handy a little bit later, because I'm going to obey the Helmholtz's principle that every talk will have at least one proof. It's going to be on the final. So That's the. So suppose that you have two really independent algebras, A1 and A2. And you have elements A1, A2 up to A2n. The odd elements belong to the first algebra. The even elements belong to the second algebra. And I know that tau of everything from from 2 to 2n minus 1 is equal to 0. So the expected values of all the variables except for possibly A1 and A2n, all of those are equal to 0. And what you want to do is calculate the product of the expected value of the product of these elements. How do we do that? There's a standard way to do this kind of calculation, which is this. You center the variables. So set AJ prime equals AJ minus expected value of AJ. So AJ prime is the centered version of the, AJ prime is the centered version of the variable AJ. Of course, this is only significant for j equals 1 and 2n in this particular case. For other calculations, you might need to do it for more than 2 variables. And denote by b the product of the middle 2n minus 2 variables. And let's look at tau of a. Do I have a pointer here? I do, okay. But let me not use it. So tau of A is tau of A1 times B times A2 and B is the product in the middle. And now you expand it by using the fact that A1 is tau of A1 plus A1 prime and A2n is tau of A2n plus A2n prime. You're going to get 4 terms, right? What was it? Inside out. I learned this from my kids. Yeah. Yeah, something like that. Okay. So you get 4 products. I write the most significant ones down. Yeah, so it's tau of A1, tau of, so if you take the constants, you get the product tau of A1 times tau of A2n times tau of B, and you get 3 more terms, okay? And you'll notice that this first term is equal to 0 because tau of B is equal to 0 according to the definition, but the other ones are all the same form actually. So one of them has a constant, so if you take tau of A1 from the first parenthesis and A2n prime from the second, from the last parenthesis, again you have a constant, a constant that factors out, and the product, an alternating product of elements with trace equal to 0. In other words, the result is 0. We're always happy when the result is equal to 0, right? So that's what you get in this particular case. Yeah, and an exercise for those of you who have not seen this kind of thing before. Suppose that n is equal to 2 and we don't make any restrictions on the expected values of variables aj. So in other words, all 4 of them might have non-zero values. Calculate the expected value of the product of the 4. You have to use the same technique, but instead of 4 terms, you'll have 16 to be precise, and not all of them are going to be equal to 0. Okay, distribution. What does one mean by distribution in this general context? The expected value distribution, as Voiculescu called it, since he has the other kind of distribution, which is the normal polynomials kind of distributions. So if there are no structures assumed on the algebra A, the distribution of a variable is simply the sequence of the moments of that variable, right? So tau of A to the n is the nth moment of A. And this sequence from n equals 0 to infinity, or from n equals 1 to infinity, if you want, because the first term would be 1 all the time, is the distribution of the variable. And I'm also going to use the formal power series sum of tau of A to the n divided by z to the n plus 1, which can be viewed again formally as the trace of the resolvent of the element A. I mean, so it's neither resolvent nor series, might make any sense, but formally we have this. So that's. I'm assuming nothing, just an algebra and an element in that algebra. Okay. So it's just a power series. But of course, if A is a Banach series, then at least the calculation makes sense for large values of Z. And the identity is correct. Not only that the series converges, but Z minus A is invertible, and all of that good stuff. And if A is W star algebra, perhaps B of H or something like that. And if A is a normal element, or even a real element, if you prefer, there's a more refined notion of distribution, which is just apply the trace, the expected value to the spectral measure of that element. And there's, of course, the obvious relation that in case, let's say if you have a self-adjoint element, then the function GA is in fact the Cauchy transform of the of that distribution. Okay, questions? Free convolution. So a little bit about free convolution here. So first, some notation here. Suppose that that A is an element in the algebra A. And I might notice that the formal series GA of Z, which is the sum of tau of A to the n divided by Z to the n plus 1. So this formal series has a formal inverse. So the way to think about it is that this series is defined for large values, an imaginary neighborhood at infinity. Okay. So KA has a formal inverse. So you see GA takes infinity to 0, therefore should take 0 to infinity. It's an inverse function. So KA, the formula is of the form 1 over Z plus a power series from n to the n minus 1. And we have the formal relationship GA of KA of Z is equal to Z. And the power series itself is the original R transform of Voiculescu. Yeah. Sounds like a crazy thing to do. And it is to some extent. But you have to be, you know, you have to take the Sherlock Holmes point of view here. That after you have eliminated everything that's impossible, then what's left is what's true. Yeah. So this is our transform of the variable A. Okay. And there's a theorem of Voiculescu that comes here, which is this. Suppose that A1 and A2 are two free algebras, and A1 variables A1 and A2 belong to those two algebras. Then the R transform of A1 plus A2 is the R transform of A1 plus the R transform of A2. Which implies that there exists an operation on distributions that says that the distribution of A1 plus A2 is a function of the distribution of A1 and of the distribution of A2, which is called the free additive convolution. And this is the theorem that I prove for you today.
So a little confused about the notation. A is the total arbitrary element in the algebra, it's not self-adjoint anything. And what kind of object is a piece of A?
The sequence of the moments, tau of A to the n. So you just have something that's what it is. And the sequence that we have right here is also a collection of numbers, which is the collection of cumulants, pre-cumulants of the variable. Yeah, so this makes in this complete generality makes perfectly good sense. And now, how does one prove it? I will use the Banach algebra context because it allows for a nice, neat proof. the extension to arbitrary algebra is not a problem. And it uses observations by Hagerup and then a rearrangement of the Hagerup observation by Franz Lehner, which gives a very nice little argument. Okay, it's reactive. So there's a lemma. So you have two free algebras again, and you have elements xj that belong to the two algebras, x1 and x2, that are invertible, and they satisfy these conditions. Tau of x1 inverse and tau of x2 inverse is equal to 1. But not only that, but x1 inverse and x2 inverse are equal to 1. So just imagine x1 inverse is almost 1 and x2 inverse is almost 1. The technical condition is just that the product of x1 inverse minus 1 and x2 inverse minus 1 has norm strictly less than 1. Then the conclusion is the lemma that x1 plus x2 minus 1 is also invertible, and the trace of its inverse is equal to 1. So this is my attempt to give everybody something that perhaps they haven't seen before. It might be disappointing, but it's proof. Well, the invertibility does, it's really a version of the, sorry, Ping, I'm in your way all the time. So this is really a kind of a variation of the resultant equation. But a variation that nobody has thought about before Hagerup. And it looks like this. So the fact that that element in the third condition has norm less than 1 tells you that 1 minus that element is invertible. Okay. Now let's factor out x1 inverse on the left and x2 inverse on the right from that expression. What do I get? Well, I get x1 inverse times, well, here I wrote out the calculation. Of course, you have to expand that product of two parentheses of two elements. You get 4 terms. But one of them cancels x1, x2, right? So 1 times 1 is 1, 1 times x2 is x2, and so on. And x1, x2 cancels x1, x2. So it's x1 inverse times x1 plus x2 minus 1 times x2 inverse. So that thing is invertible, but x1 inverse is invertible, x2 inverse is invertible. Therefore, the thing in the middle is invertible. So that's invertibility. Now trace calculation. Okay. This also allows you to calculate the inverse of x1 plus x2 minus 1 inverse. It's a power series. You get x2 inverse times the inverse of that thing in the left-hand side times x1 inverse. Expand it using the, what is it? I'm sorry? Yeah. Okay. Well, anyway. So all of those things are products. You notice those products have the property that the elements in the middle alternate out from the alternating algebras, and they have traces equal to 0. Okay. So this tells you that every element in the sum has trace equal to 0 except for the first one, which is exactly trace of x2 inverse times trace of x1 inverse. And that's it. Did I do something wrong? All right. So this is where the sample calculation comes in, right? So it's an alternating product, but the first and the last elements don't have traces equal to 0, but the ones in the middle do have traces equal to 0. Yay. Now let's go back to the theorem. So suppose that Z is very large, and Z1 and Z2 are chosen so that GA1 of Z1 is equal to GA2 of Z2 is equal to 1 over Z. Remember what GA of Z is? The expected value of Z minus A inverse. So we're in a Banach algebra, so this is roughly like 1 over Z. Z is very large. So in a specific sense, what I choose is Z1 equals KA1 of 1 over Z, and Z2 is KA2 of 1 over Z. That's my choice. Okay. And now I call X1 Z1 minus A1 divided by Z, and X2 is Z2 minus A2 divided by Z. And I say that this satisfies the hypothesis of the lemma. Why? Well, that's the choice of Z1 and Z2. That's right. So if you look at X1 inverse, that's Z1 minus A1 inverse times Z. But the trace of the inverse is 1 over Z, which gives you 1. And not only that, but this X1 and this X2 are also very close to the identity element of the algebra. Z is very large. So they satisfy the hypothesis of the lemma, and therefore the conclusion of the lemma as well. So the conclusion of the lemma is that X1 plus X2 minus 1 is an invertible element, and the trace of the inverse is equal to 1. And the conclusion, I'm going to write it as, so the trace of the inverse is equal to 1, but if I take out the Z as a factor, what I conclude is that tau of Z1 plus Z2 minus Z minus A1 plus A2, the inverse of that has trace equal to 1. So what? Well, so what comes here? Because this tells you that GA1 plus A2 of Z1 plus Z2 minus Z is 1 over Z. The definition of G. But what was Z1? Let me rewrite it again using inverses. I say that this relationship is KA1 plus A2 of 1 over Z is Z1 plus Z2 minus Z. But Z1 is KA1 of 1 over Z, and Z2 is KA2 of 1 over Z. Yeah, it's a little mystifying as a proof, but it has the advantage that it can be presented in a short amount of time. The original proof, I should say, contains a lot more mathematics than what I've done here. But it's a proof. So there. Now to come back to perhaps Brian's concerns here, let's come back down to earth, and let's say that oh, well, maybe not yet. We'll come down to earth. We'd like to talk about unbounded variables. Sometimes it's in probability it's useful to talk about unbounded variables. Sometimes the most important variables in probability, classical probability, are unbounded random variables. Gaussian variables are unbounded. So you would like to be able to deal with this kind of thing in this context. You'll notice that the proof that I have just shown you here survives if the elements AJ are not necessarily in the algebra AJ. But what you need really is that the resolvent belongs to the algebra AJ. So maybe the whole algebra A lives inside the bigger algebra that contains these X1 and X2, and A1 belongs to the algebra big A1, not only in this generalized sense that the resolvents belong to the algebra. Okay, so perhaps the expected value is not even defined on the bigger algebra. What you need is the expected values of resolvents. So so the proof survive in this context. So of course the most interesting situation is the case of a W star algebra, right, or C star algebra if you want. B of H, for instance, a self-adjoint element, possibly unbounded, then this whole theory applies fine. In the sense that that you have this GA is no longer power series. That's a sad thing, perhaps, that you just cannot deal with power series in this context. So GA of Z is the expected value of the resolvent of A at the point Z. And this is defined whenever Z is not a real number. I take typically will take my Z to belong to the upper half plane, which I denote here by H, and GA of Z is an element in the negative half. So that's very nice. And this GA can be expressed in terms of the distribution of A viewed as a probability measure on the real line rather than a sequence of measures, sequence of moments. Rather than a sequence of moments, actually have a measure, which is that expected value applied to the spectral measure of A. So that's GA becomes in this case a Cauchy integral or a Stieltjes integral or a Borel integral, depending on who you ask. That's all three have considered. Actually, the first to consider this kind of integral was probably Stieltjes. But looks so much like a Cauchy integral. Of course, it's missing a 1/2 pi I in front, so it's a. I'm sorry? I don't know. I think by now it's tradition. Yeah? So we call it the Cauchy transform, so for instance, if you write it as integral of 1/t minus z, then it has a different name. I forgot what it is. Yeah. Important thing about the Cauchy transform is that it allows you to recover the measure. It's you remember what it is?
I thought that the sign is either
multiply it by -1 and follow it to the end.
Yeah. Actually, you know, if one wants to be historically corrected, the Stieltjes integral was integral of 1/z plus t. And it was only for measures defined on the positive. But none of these gentlemen is going to come and complain, so it's not. And one important observation about this Cauchy transform is that if you take its imaginary part and divide it by pi, you get minus the Poisson integral of the measure mu. And therefore you can recover. In principle, we can recover the measure mu from the Cauchy transform. Okay. One more important fact that I want to point out here is that the angular limit as z goes to infinity of z times GA of z is equal to 1. So in some sense, GA of z still behaves like 1/z, but only when you approach infinity. What does angular limit mean in this particular case? Well, we have to take an angle. You know, I'll write it a little later. And one interesting trivia fact here, perhaps, is that if you have an analytic function g from the upper half plane to the lower half plane, which does satisfy this asymptotic, then that function is of the form Cauchy transform of self-adjoint upper, or Cauchy transform of Cauchy integral of a probability measure on the real. So that one says probability measure. One in the. Okay, some examples of R transforms. So some examples, computable, and these are all associated with measures on the real line. So let's say that R of z is a constant. So let's go down the path of how one goes from G to K. You know, so if you know the R transform, then you know the K transform. K of z is C plus 1/z, right? And then G of z is the inverse function of this. Solve the equation. The inverse turns out to be 1/z minus C. What's this the Cauchy transform of? It's the Cauchy transform of the point mass at the point C. Okay, so that's let's take R of z to be a different kind of constant, namely the I. The same calculation is going to give you that. So again, you calculate K, then you calculate G, solve the equation. There's no big deal. G of Z is 1 over Z minus I, which is written on the right-hand side, X minus I times Y plus I plus. The reason I want to write the real and imaginary parts because I'm interested in the imaginary part of this function. Right, the imaginary part is y over x squared plus y plus 1 squared. And you are interested in what happens with this as y goes to 0. And this is what happens. This function is the Cauchy transform of the Cauchy law. What a coincidence. That one really is the Cauchy law. He had not only this one, he had a family of measures with exponential Fourier transforms. This is the simplest of them. Okay. One more example. R of Z is equal to Z. Then Z of Z is G of Z plus 1 over G of Z, which, I mean, K of Z is, the equation K of Z, G of Z equals Z gives you that equation, Z equals G of Z plus 1 over G of Z. So we have to solve for G of Z. It's a quadratic, but we know how to do that. So you get G of Z equals Z minus the square root of Z squared minus 4 divided by 2. You can ask, why not plus? Why minus? And the truth is that doesn't make any difference. Unless you say what you mean by the square root. Because square root has 2 values. So you choose the one, you choose you choose that value which makes the square root of Z squared minus 4 positive for large real Z. And again, by looking at imaginary part and taking y equal to 0, you discover that this is the standard semicircle law. Is this it? Oh, yes. Okay. That's the standard semicircle law. They were known as the free Gaussian sometimes, which is 1 over 2 pi square root of x squared minus 4 on the density equal to that on the interval from -2 to 2. And, there's one more that has a nice simple calculation, which is R of Z equals 1 over 1 minus Z. And this corresponds to the free Poisson law, which is also known as the Marchenko-Pastur. Think?
Can you tell us, just a simple answer, what kind of function am I allowed to put on the right-hand side? R is equals something, and what kind of function am I allowed to put that will give me properly measured?
I can tell you one class of functions that will surely give you an answer. Namely, if you have a function in if your R of Z is a function defined on the upper half plane with values in the upper half plane and analytic, and it has angular limit at infinity equal to 0. Actually, if you divide it by Z, you get an angular limit equal to 0, then that is the R transform of something. I'm sorry, if you divide by Z, finite limit. Not too bad. Something that's not too bad. Something that's reasonable. I'm not saying it should have, but if it does, if it's analytic in the entire half plane, and it has that is a sufficient condition, and that's a description basically of the infinitely divisible measures relative to a free convolution. I wasn't going to go into that, but you drew it out of me. Okay, all right, thank you. 4 minus x squared, yes, thank you. So that's the density is square root of 4 minus x squared, not x squared minus 4. You want a probability measure, not I times of probability measure, right? So, yes. Yeah, you can multiply it by something. Yes. Yeah. You can just take this function and multiply it by lambda. So this is the case in which you get a variance equal to 1. So otherwise you might so lambda, the variance that you get in the Poisson is that's the parameter that you get there. Yeah.
About characterizing analytic functions which are transformed.
Yeah, there is a theorem. So Voiculescu wrote a theorem on this particular subject, but it's not a usable theorem. So the theorem comes essentially to saying that you have this function R of z or K of z, let's say, and the function K of z has an inverse which extends to the entire half plane. That's satisfactory.
Right, well, it's just that for Cauchy transforms, there is a very simple description.
Yeah.
So hard to look the other bench.
Inverse function.
It's a problem. I mean, it's the same. It's really, what you're asking is really the same question as to what is the characterization of the Fourier transform of a measure, and that's not an easy question either. So you have so again you have a class of functions that have a class of measures that you can characterize by the fact that they have the Cauchy transform written in a specific form, like let's say the Levy-Hinchin formula, and those give you infinitely divisible measures. And then there are others that you cannot really. So that's really so a lot of the interplay, even in classical probability, a lot of the interplay between the measure and the Cauchy the R transform or the Fourier transform plays on the fact that you really cannot tell all that much about it. So for instance, you want to characterize the tightness of a collection of measures. You want to characterize it in terms of Fourier transforms. Well, it's not that easy. So we have.
That's good to keep some people in the job.
No, that's the job has been done, but so we know how to do that approximately speaking. Yeah. So you see that the number 1 there at the bottom is my planned end for the lecture. So this is your exercise. Of course, I have 5 more minutes. So you want me to go longer? Well, what happens after this? No, nothing happens. So I push the button, nothing. So it had to stop. Can we do something to make it move? Have we done something here? You probably have to make that nice little song. Yeah. Well, no. Let me leave it for next time because okay. It's conceived in a certain fashion.